Hello everybody, happy Halloween and all. Today's episode we're going to be going over electron transport chain, ETC. Tune into other videos at Adam the Science Tutor. So, a little things about the electron transport chain. It's kind of our last ditch effort in the mitochondria to get energy and get energy through ADP to ATP. It's found mostly in the inner mitochondria, and so that's where most of this is going to be occurring. And the complex 2 is going to be found in the matrix, but we'll get to the complex 2 in just a bit. So we're gonna take on this question at the end, but primarily, if you give it thought, when do we need energy? It kind of depends on our body. There's no direct time periods. If our body needs more energy, we're gonna put it through the electron transport chain. If we have oxygen, because we need oxygen, it's dependent on oxygen levels, and it also needs ADP. So it needs energy to make energy. So it needs adenosine diphosphate to make into ATP. So that's very important as well. So let's kind of get started. It's oxygen dependent, so that's why we need oxygen. So for electron transport chain, there's going to be different complexes, and they're protein complexes. So we're going to have complex 1, and it's going to push hydrogens out, and it's going to go to complex 2 and push electrons on from complex 1, 2, 3, 4, and then eventually 5, in which and it's also called the ATP synthase. That's what I commonly used in undergrad, but just to make things simple, we're going to go over each of them, but it's the 5th complex. And that's kind of the complex that makes the ADP turn to ATP. So cool. Yeah, electrons are going to be moving from complex to complex. So kind of just like a regular tube. It's going to go from one protein to the next. And these electrons are going to keep moving, and the hydrogens are going to pump out, creating an electron gradient. So that's commonly referred to in class as well. So electron gradient. And it's created by the hydrogens moving out and creating a basic environment in the inner mitochondria and a more acidic environment in the matrix. So complex 1, another name for it is NADH dehydrogenase. And if you guys remember in my other videos, I mentioned that dehydrogenase is an enzyme that removes a hydrogen. So it's going to take an NADH molecule, which we've gotten from different complexes like the Krebs cycle and whatnot, and it's going to make it into NAD+. The electrons from this, which is very important, are going to go into the complex 1, and they're going to go into your FMN. So these are fibrin mononucleotides, but FMN is easier. So, and it's going to pump out, so it's going to go to FMN, and then it's going to get rid of our 2 hydrogens, and that's going to be our first hydrogen pump, and those are going to go outside. So it's going to make the inner mitochondria more basic, and it's going to make the matrix more acidic. And so yeah, it's getting reduced, and electrons are also going to flow out. We're going to have another molecule, but I would say the most important is NADH and the FMN2. But we have some sulfur as well, and these guys are going to help transfer the electrons. So it pulls the electrons from the FMN. It doesn't want the hydrogens, so the hydrogens get kicked out through the pump, but it's pulling these electrons, and these electrons are being passed on to our complex 2. So that's very important. I'm highlighting the important things coming out. And yeah, so that's NADH dehydrogenase, another name for complex 1. So it's a very important. So let's go on to complex 2. So complex 2. Complex 2 is another name for it is called succinate dehydrogenase. Succinate is going to turn to fumarate. We see this kind of reaction in the Krebs cycle, and it works similarly. So it's called succinate dehydrogenase. And dehydrogenase, once again, it's a removal, it's a reduction, it's a removal of hydrogen. So we're going to get succinate, and it's going to turn to fumarate. Cool. And then we're going to be using, I don't know if you guys remember, but in the Krebs cycle, we go through it, and succinate to fumarate is done by succinate dehydrogenase as well, and we get FADH2, and that's going to turn to FADH. Or in the Krebs cycle, it turns from FADH to FADH2. And a lot of these are reversible so that they're happening all the time and we're getting the energy we need. And then right here, we're going to do coenzyme Q. It's also called euquinone. So coenzyme Q. And this can happen at complex 1 as well, but it's usually referred to as in between complex 1 and 2. I just showed it on complex 2 just for easier sake. But coenzyme QH2 is called euquinol. And that's where we're going to get our hydrogen pumped out of. And it takes the hydrogens it pulls the hydrogens off these FAD molecules, and then we're going to release them. And it's going to keep on the electrons and push the electrons out. And we'll see these coenzyme Q or ubiquinol later. I'm moving over this complex because it'll be easier to see, or easier to picture if it's in between 1 and 2 like it's supposed to. I don't know why I drew it on this side, but let me see if I can lasso it. Yeah, move it over. But all you need to know with complex 2 is that, we have coenzyme Q, which is it's one of the only molecules in the electron transport chain that is not a protein, and it's used to taking the electrons from complex 2 or 1 and pushing out hydrogens as well. So it's very important. So I'm keeping out to moving myself. And just to reiterate, either happens in complex 1 or 2. That's just what happens. And there's not a direct pump on complex 2. That's another important thing to keep in mind. But we pass on the 2 electrons. So let's move on to complex 3. Complex 3 is going to be called Cytochrome C reductase. Sorry. So Cytochrome C reductase, and it's going to be kind of what we'd expect, or cytochrome reductase. It's going to be what we're expecting. So you're going to have cytochromes turned and reduced. Reduced means you're going to be gaining electrons. So cytochrome A is going to be the active form. So cytochrome B, and then it's going to be another cytochrome BA. So it's going to be the active form. And then I'm going to have to go to cytochrome A again. One sec. Yeah, it's cytochrome A, so it's active. Cytochrome B is inactive. And then it's also going to have these FES porphyrin rings. And what's interesting about cytochrome and FES porphyrin rings is that they have heme groups. Heme groups are cysteine rich, and they can hold onto iron. So that's kind of a cool thing, and it's interesting about complex 3. And then we have our cytochrome C. Cytochrome C is extremely, extremely vital and important, and it can hold 4 electrons, which is it's going to be important for complex 4. 4 electrons allows us to make our 2 water molecules, which will be a part of our end product of the electron transport chain. And like all the other complexes, we're moving the electron gradient down the line. So it's going from complex 1, complex 2, and now it's at complex 3, and we're pushing more of these electrons. We're pushing more of these electrons down the gradient. So it's going all the way down. It's going to go to the ATP synthase, which is their end. I wish I could minimize my face sometimes so I don't take up space, but it makes it kind of hard. All right, cool. So we do have a hydrogen pump here. The hydrogen pump is here, and we're getting rid of our 2 electrons. Cool. So now we're going to go over to complex 4. So complex 4, another name for it is called Cytochrome Oxidase. I told you guys already, or I gave you guys a sneak peek saying that we're going to create 2 water molecules, H2O. So we're going to get oxygen, and we're going to get hydrogen from the matrix, and we are going to create water molecules. And we're also going to have Cytochrome A and Cytochrome B and Cytochrome C. Cytochrome C is extremely important because it carries our 4 electrons, which we need. So drawing all our cytochromes. And then we're going to have to draw our Cytochrome C on the outside. We're pulling these hydrogens from the inner matrix, and we're putting them into our mitochondrial matrix. So we're going to have 4 hydrogens total. We're going to get 4 hydrogens from our Cytochrome C because it carries 4 hydrogens, which is important because we need 4 hydrogens and we're going to need 2 oxygen molecules. And like I said earlier in the video, oxygen molecules are essential for the electron transport chain to work. Without oxygen molecules, we cannot, the electron transport chain won't start up, it won't work at all. So it's very important. So just know for complex 4 that Cytochrome C carries over 4 hydrogens, and we're going to get oxygen from the environment, and it's very important, it's essential. We can't do this under anaerobic situations, and we're going to create 2 H2O molecules, and we are also going to shift our 2 electrons down the line into our ATP synthase, or complex 5, which is important. So yeah, complex 1, we're pushing 2 electrons, Everything's getting reduced, and we're creating a certain environment with these hydrogens. We're making the matrix more acidic and the inner membrane more basophilic, so that we could create a gradient for these electrons to move down. There's no direct H plus pump here on complex 2. There is a pump on complex 3, and we're still pushing our electrons down. So yeah, so let's go talk about complex 5, or what is called the ATP synthase. ATP synthase is doing exactly what it sounds like. Synthase is a creation. We're going to create our ATP there. And ATP synthase is made of a 2-protein molecule, which I'm going to draw out in just a bit. So now what I just kind of said, we're going to make ATP synthase. Or not make it, but we're going to talk about ATP synthase and how it's able to make our ATP. So complexes 1, 2, 3, and 4 were our electron transport. Complex 5 is for ATP creation. So right now I'm drawing one of the protein units, and that's F0. So F0, and then the axe-looking shape is F1. So hydrogens are going to go and almost turn, we're almost going to turn this ATP synthase, and it's going to spin it so that these electrons can get pumped. So it can get pumped, and then we're going to make ADP into ATP. So it creates an electron gradient. This whole thing is called ATP synthase. So yeah, it's complex 5, Roman numeral. And these electrons are pretty much just getting pushed out. So they're getting pushed out and they're getting turned, and these ADP molecules are going to find these electrons, and they are going to create ATP. So very cool. We make our ATP, which is our energy source. So we use ATP for energy because we could break phosphate bonds, and phosphates like to activate different things. So that is the end of electron transport chain. There's not much else to cover. There's different things that can inhibit, or different poisons that inhibit the electron transport chain, such as like monoxide. Let me see, I have a note somewhere with this. Let's see. Okay. I can't find it. But there's different poisons that are going to be able to affect and make holes in the system. So when we need energy is the answer to when. So whenever our body needs the energy. Thank you guys for watching, and please tune in again to Adam the Science Tutor.